All right, guys, let's go ahead and get started. And we're going to pick up where we left off. We're going to pick up where we left off the other day. We are in the middle of hydration of alkynes. So I showed you how we go about the process of hydrating an internal alkyne, right? And if you remember, basically what happens is we use the traditional mechanism of hydration, like we learned in chapter 10, to form something called an enol, which tautomerizes into a more stable keto form, right? We haven't done anything with terminal alkynes yet, all right? Now, if you remember, a terminal alkyne is going to have the triple bond on the end of the molecule, all right? That's why we call it terminal. All right, so if you want to do a hydration here, it's very, very similar to what we did with internal, with just a couple of little things to remember. Number one, like we mentioned the other day, we have to have a little bit of help here, right? We have to have some mercury sulfate as an extra catalytic agent to sort of get this to go, even though it doesn't actually show up in the mechanism. All right? Mechanism-wise, you're still going to be limited to H2O and H2SO4. All right, so let's walk through this. Somebody tell me what's going to happen. All right, we're going to get an H from the H2SO4. What's it going to do?
They can attach to the right carbon because they create the lesser, less stable carbon.
I'm sorry.
Sorry.
Can you say it a little louder? I just couldn't hear you.
So would it hit the right carbon because it is the least stable carbocation?
Most stable carbocation.
Yeah.
Yeah, it's going to attach right here specifically because this is still going to follow Markovnikov's rule, right? We're going to go through the most stable or substituted carbocation. If you want to remember the little trick with, whichever carbon has the most hydrogens gets more, that works too, right? That is one bit of a difference between hydration of a terminal alkyne and hydration of an internal. Sometimes with internals, Markovnikov's rule might help you. Actually, no. Markovnikov's rule will never apply with internal because they're always just going to be monosubstitute. Right here, with terminals, the decision is pretty easy. You always go with the end carbon, right? The end carbon always gets the H+. And that's going to mean that this one is always going to get the water. And so once again, you see, just like last time, you're going to make an enol, right? The OH of your enol is always going to be on the internal carbon, not the end one. That's going to be an important distinction to make when we get to our next reaction as well. All right? So this is our enol. What do we know about enols? How stable are they? Not very. What do they like to do? They like to tautomerize. Yeah. Sometimes we know the mechanism of tautomerization. Sometimes we don't. In this case, we do. And it's going to be exactly like the method that we used last time, right? H2SO4 will protonate that double bond according to Markovnikov's rule again. And then leaves you a carbocation. What happens now? Y'all remember? What's that? I'm sorry. That's the bad thing about math. I can't tell who's talking to me. Was it you, Josh? Okay. What'd you say? It turns into a ketone. How do it, in terms of mechanistic steps, how does it get there? What's that?
One of the
Electron pairs?
yeah.
Yeah.
Go into the bond.
Yeah, it forms a resonance structure. Yeah, forms a resonance structure when a pair of electrons swoops down from the oxygen. And then the last thing that happens is you pluck off this guy. Boom. And that's how you get your keto form, which in this case gives you a ketone. I know going through the mechanistic steps seems a little bit repetitive sometimes, but again, I can't overemphasize how important getting good at this is. So I like to err on the side of doing it over and over. Okay? Are there any questions about how we got through that mechanism? All right. I gave you a little bit of a general guideline the other day for internal alkynes. When you do a hydration of an internal alkyne, what do you always get? Look in your notes if you need to. What type of molecule do you always make? Ketones, yeah. You have a similar guideline for hydration of terminal alkynes. Well, what type of molecule did I just make? You tell me. What is that? It's like also a ketone. However, it's a very specific type of ketone. With terminal alkynes, you know how ketones have this general form? Carbonyl carbon with 2 R groups. Whenever you do a hydration of a terminal alkyne, at least one of these is always a methyl group. And you can see that right over here. We have a methyl group. Terminal alkynes always form what we call methyl ketones. Methyl ketones just simply meaning that one of your R groups is a methyl. Internal alkynes produce just ketones in general. Sometimes they produce methyl ketones, sometimes they don't. It just depends on what type of material you start off with. But with terminal alkynes, you always get methyl ketone specific. So that's a nice little sort of guideline or a little bit of a cheat sheet memorization type thing that might also sort of help you double check your results. Okay. That make sense? Are there any questions about hydration of alkynes? All right. All right, we got one more addition reaction of alkynes to go over. And again, it's something we did with alkenes. It's going to be hydroboration oxidation. All right, and it's going to work the same way using the same reagents as we did last time. I'm going to start off actually here with terminal alkynes, because that's where you can see sort of the clearest distinction here of what happens. So let's look at a terminal alkyne. And you remember hydroboration oxidation has 2 steps, right? We start off with BH3 for the hydroboration part, and then hydrogen peroxide in the presence of OH minus for the oxidation. All right. So what do you remember about the hydroboration step of alkenes? What was special about it? No, the magic is in the oxidation.
It goes in one step.
It goes in one step, okay.
So it forms a box.
Forms a little box structure. Josh, do you want to say something? Does not follow Markovnikov's rule, absolutely correct. Yeah. Basically, this is the one where you had complete syn addition, right? Where, no matter what, this H and this BH2 approach from the same side, right? And end up with a little box-shaped intermediate. Like that. This works exactly the same way. The only difference is there's an extra pi bond remaining. And when all is said and done with that step, you form your hydroborane. Again, just has an extra pi bond. All right, so that's the hydroboration step. Then it's the oxidation. And this is where the magic came in. What, other than magic, what happened in the oxidation step? We didn't learn the mechanism because it's basically not well known. But what was the end result of the oxidation step? Yeah, basically the BH2 gets replaced by an OH. And that's what happens here as well. All right, so you saw with like a terminal alkene, that would just give you a primary alcohol as your product. However, this isn't just an alcohol. What type of material is that? What type of functional group do we have there? It's an enol, yeah. That means this one's going to take a little bit more examination because we know enols are not stable. Enols like to tautomerize, right? This is one of those occasions where we don't know the mechanism. I told you, sometimes we know the mechanism of tautomerization, sometimes we don't. With hydration we did, here we don't, so we got to use magic. And also a bit of deductive reasoning to kind of figure out what's going to happen, right? I think we can probably figure this out. How do two tautomers differ from each other? What do we say? They differ in two respects.
Placement of a pi bond and one hydrogen.
Placement of one pi bond, placement of one hydrogen. So that means whenever we draw our product here, this carbon-carbon pi bond is going to be somewhere else. Where else might that pi bond be, do you think, in the final product?
The oxygen.
Yeah, if you follow what happened last time, it's going to be with the oxygen. And that is true. All right? Where do you think we're going to have a sort of a transfer of an H from? Go by the pattern you saw last time. Where did the H disappear from in the last tautomerization? It was disappeared from the oxygen. And that's what it does here. Where did it appear last time? Sarah, are you pointing with your pencil? I saw, adjacent carbon, right? So this carbon is going to basically, for all intents and purposes, pick up a hydrogen. You can almost think of it like this one just goes over there, all right? So you end up with that. This is a carbonyl with an R group, and it's also got an H over there. That H has always been there. It goes up here too. What type of functional group is that? Do y'all remember from IR spectroscopy? It's another one of the carbonyl compounds, not a ketone.
Carboxylic acid.
Not a carboxylic acid. Those have OH groups attached to the carbonyl carbon.
Formal group.
Not going to be a formal group. A formal group only has one carbon.
Formaldehyde.
Formaldehyde is a specific aldehyde that has one carbon. However, what type of functional group in general does formaldehyde belong to? Aldehydes, yeah, and that's what this is. This is an aldehyde. Yeah, remember, if it has this group in it, C double bond O with an H attached, that is an aldehyde. Right? If you have a terminal alkyne and you do hydroboration oxidation, you always get an aldehyde. And that's different from what we just saw, right? If you do hydration of a terminal alkyne, you get a methyl ketone. You do hydroboration oxidation, you get an aldehyde. So that's a way for you to sort of be strategic when planning a synthesis. This one's anti-Markovnikov, hydration is Markovnikov. All right. Y'all see how we got there? The reasoning, does that make sense? Are there any questions about how we did this? All right. All right, so let's take a look at an internal alkyne here after I get this erased. Let's see, I'll put it right here. An internal alkyne. Okay. All right. I'm not necessarily going to go completely, I don't know, we'll see. I'm not going to show necessarily all the steps of mechanism, unless just the discussion takes us there naturally. I want to ask you what you think is going to happen based off of the structure that you're given and the reagents you're given. What's the first step of hydroboration oxidation always going to be? It's going to be the one that has the number 1 written next to it, right? I think that's true. First step's your hydroboration, right? So you know you got 2 carbons in a triple bond. One of them is going to get the H, one of them is going to get the BH2. Now, what can you tell me about this particular situation? Which one's going to get the BH2? Or we don't know. What's that? Both of them? Who says left? Who says right? Who says both? Who says neither? Who's just waiting for me to tell you? Thank you for your honesty. All right, well, before, when we did this with the terminal alkyne, we basically used steric hindrance, right? We saw one of the carbons involved just had nothing but H's attached to it. The other one had an R. Here, they have the same level of substitution, right? So what this means is there's really nothing preventing hydroboration of either one of them. So this is a case where you're going to get a mixture. Right? If I had given you a symmetrical one, like that, then, again, BH2 would go on either one of these, but they're the same, so it doesn't matter. But here, it does. All right, so what you're going to see with internal alkynes is that you're going to be able to hydroborate, I guess that's the word, either one of the carbons involved. If it's symmetrical, it doesn't matter. But if it's asymmetrical, that means you're going to get a mixture of carbons. So if you're thinking ahead here, that means you're going to end up with two different types of enols. That means you're going to end up with two different types of ketones. Okay. So hydroboration oxidation of internal alkynes always gives you ketones. If it's an asymmetrical alkyne, you'll get a mixture. Okay? Does that make sense? Are there any questions about the reasoning behind that? Are there any questions about any of the addition reactions that we've gone over? All right. Hey, guess what? That's all the addition reactions of alkynes. Woo! However, unfortunately, it's not all the reactions of alkynes. There's actually something else we can do that's not an addition reaction. But it's going to be super duper important. This is going to be extremely valuable to you guys whenever you do synthetic questions. All right. All right, so let's say we have, and this is only going to apply for terminal alkynes. This does not apply for internal. This is only terminal. All right. Let's say we have this. All right. I'm going to draw out that H right there because it's going to be important. Think way, way back when to chapter 2 of Organic Chemistry 1. All right, that's where we talked about acidities. If you remember the stuff that we learned in that chapter, you would know that this hydrogen right here on that terminal alkyne group is going to be a bit more acidic than any of the other H's in that molecule. This H is easier to lose than any of the ones over there. Why was that? What's that? Yeah, S character, right? It was a hybridization effect, right? That means these can be, terminal alkynes can be acidic. They can be acids. Not very strong acids, but they can be acids. So if you have a strong enough base here, the base can actually pluck off this hydrogen. Right? So for example, let's say we had NH2 minus, that's the amide ion. Very, very strong base. We add that to this terminal alkyne, it can pluck off that hydrogen. And it'll leave this behind. That's a very important species. Bless you. That is called the acetylide ion. And it doesn't matter how many carbons are in it, 2 carbons, 3, 4, 5, whatever. It's still called an acetylide ion. All right. Bless you. Tell me you're allergic to organic chemistry. Or maybe that smoke that's seeping in. Can you guys smell it too? Actually, I can't smell it anymore. It's like I've gotten used to it, which is probably bad. But yeah, it reeked when I came in. Okay. Yeah, this is going to be an extremely important material because this is going to give us a tool to extend carbon chains, to make them bigger. Right? Acetylide ion a good nucleophile. And that makes sense, right? You got a negative carbon. Negative species, especially carbon-based species, tend to be very, very good nucleophiles. They're attracted to positives and partial positives. All right? So let's say we had this. Let's say we had that acetylide ion. And we put in an alkyl chloride with it, 3-carbon alkyl chloride. What do you think is going to happen? We add these species together. Think mechanism. What's attracted where?
Maybe a partial positive on the carbon attached to the chlorine.
Yeah, absolutely. There's a partial positive sitting right over here. It's just that carbon's attached to a highly electronegative chlorine. All right, how's that going to help us out? What's going to be attracted there?
Nucleophile.
The nucleophile, this negative charge, right? Yeah, this is just a good old SN2 reaction. This is just like we learned back in chapter 7, right? Strong nucleophile, alkyl halide. You just haven't seen this used as a nucleophile before. Yeah, this is a straight up substitution. Cl minus is going to leave. And what that means is that carbon chain, which was 4 carbons originally, gets extended to 7 because we have the addition of 3 more carbons right over here. And it converts that terminal 4-carbon alkyne into an internal 7-carbon alkyne. Pretty cool, huh? You guys are gonna hate this during synthesis. Straight up honest, but it's really, really useful. There aren't that many ways that we're gonna learn to extend carbon chains. This is the first one. We'll learn another type. Gosh, I don't know. Probably like chapter 20 or something like that. Can't remember, but later on. But this is going to be the dominant one that you use for right now. Reaction of acetylide with alkyl halides. Can I erase? Does that make sense? All right. All right, I think we got 5 minutes. I think I can find a quick practice problem. Okay, so let's say we're doing a synthesis. 1, 2, 3, 4. Say our target compound is this. This is what we want to synthesize. And we have to start off with this. Plus anything else that we need. All right, how would we do it? It's a 2-step synthesis. One thing that I always tell you guys for syntheses is that you always need to take stock of what you have and what your target is, right? Part of this is going to be taking an inventory of carbons, right? So get used to that. Look to see how many carbons are in your starting materials, how many carbons are in your products, right? Here we want 5s, or we want 5. Beginning we want 2, right? That should tell you in your mind, I need to add carbons. How many ways do you guys know how to add carbons? 1. It's just one that we just did, right? So how would you approach this?
Add a strong base.
Add a strong base, we got a terminal alkyne. NH2 minus works great. It's not the only one. You can also use turkey topside in the presence of DMSO. So I'll just do that one so you can see there's a couple of different types. That will produce acetylide. And then what?
Did you add a chain with the amount of carbons you want to add, but then with like Cl minus or like Cl attached to it?
Okay.
And DMSO.
All right. So you want to add an alkyl chloride with the targeted number of carbons. How many carbons will that be? 3. Okay. So you want a 3-carbon unit with Cl. Should the Cl be in the middle? Should it be on one of the ends? It's going to be the end. Yeah. Pay close attention to where you put your halogen. If you had your Cl in the middle, that would give a different type of substitution product. So yeah, voila, there you go. That's a quick example of how you can use this in synthesis. We're going to do some more advanced examples too. It's not always quite as obvious as it is here, so we'll save that for Wednesday. Quick update on sapling again. I've contacted my rep through email. I've used the customer service submission bank online. I have left a voicemail with my rep on Friday. So I'm hoping I get something back from him today. So just hang in there, but keep plugging away on those other practice problems. They'll give you the practice that you need for the moment. All right, I will see you all later.